Welcome to the Deep Dive. We're the show that pulls back the curtain on the things that, well, actually run the modern world. We're talking about the invisible materials, the supply chains, the foundational chemistry that you rarely think about.
Until they become a crisis.
Exactly, until they become a crisis. And today, we are diving right into the core of one of those crises. Rare earth elements, or REs.
These are the 17 elements that are just mandatory inputs for everything high tech, from the tiny actuators in advanced missile systems all the way to the big motor magnets and EVs and wind turbines.
And the context here is really a 50-year masterclass in strategic, state-driven industrial planning. It's the story of how one nation, China, took a geological advantage and turned it into this just overwhelming economic and technological superiority.
Right. And our focus isn't just on, digging dirt out of the ground. It's about how control over the sophisticated processing and the high-value manufacturing of these elements became a critical geopolitical weapon.
The ultimate choke point for the entire global tech supply chain.
That's our mission today. We want to trace that journey step by strategic step. We need to look at the science, the industrial policy, the strategic decisions that allowed them to achieve what is, it's essentially a near total global monopoly over the most crucial materials of our century.
So to set the stage, we have to start at the very beginning, with the foundational breakthrough that really made everything else possible. Our research for this deep dive really kept coming back to this one story.
Imagine China in 1971. The chaos of the Cultural Revolution was still ongoing, universities were closed, and intellectuals were viewed with suspicion. Yet, in a corner of Peking University, a tall, thin chemist with a deep love for the ancient game of Go and martial arts novels, Xu Guangxian, received a strange and urgent task from the People's Liberation Army.
And his mission?
His mission was to solve one of the most intractable problems in chemistry: purifying rare earth elements. These elements were called rare earth, not because their reserves were scarce, but because separating them from each other was, at the time, an almost impossible challenge.
So the military needed them for something specific?
Urgently. They needed these ultra-high purity samples for R&D on new battlefield laser equipment. So Xu Guangxian and his wife, Gao Xiaxia, they worked secretly in their lab. The final solution, though, it was unexpectedly simple, almost a kind of challenge to the global chemical community.
How so?
They didn't use any expensive high-tech equipment. Instead, they used low-cost hydrochloric acid and simply constructed plastic storage tanks to achieve a revolutionary purification. The mixed rare earth raw material was injected from one end, and after combining with different solvents, the high-purity rare earth elements were precipitated out from different outlets on the other end.
So it's more than just a scientific breakthrough.
Oh, much more. It was the blueprint for global hegemony. The technology was so incredibly low cost, it allowed China to produce rare earths at this astonishing speed and scale. And that ultimately led to them monopolizing 90% of the global supply.
So you go from this simple chemical experiment, run by a rehabilitated scholar with cheap materials during a turbulent time,
to today's strategic weapon that holds the supply chains for EVs, wind turbines, even the most advanced AI chips, completely hostage. This 60-year path is just far more complex and profound than we imagine.
That story is incredible. It just reframes the whole narrative, doesn't it?
Yeah.
This dominance wasn't an accident of geology.
Not at all.
It was a victory of specific, targeted, low-cost chemistry applied at the perfect moment. So we had to start there, with the science, because without that initial breakthrough, none of the rest, none of the economic or political dominance would have followed.
That's absolutely right. The core problem, and the reason Western industry saw REs as too costly and frankly too marginal for decades, it all lies in their fundamental chemistry.
You mean the fact that all 17 of them are so similar?
Exactly. The 17 rare earths, which include the lanthanide series, are chemically almost identical. And this is due to a phenomenon called lanthanide contraction.
Lanthanide contraction. Okay. That sounds like it's straight out of a textbook, but that's the key to the whole problem, isn't it?
It is. As you move across the series on the periodic table, the outer electron shell, its configuration stays the same, so their chemical behavior is nearly identical. But the inner electrons do a poor job of shielding the growing positive charge of the nucleus.
Which means the atomic radius starts to shrink just a tiny bit.
A tiny, tiny incremental bit. And that minute difference in atomic size is the only lever chemists have to pull them apart. It's like trying to sort a basket of perfectly blended eggs that only differ by a millimeter in circumference.
So for decades, the West, the US and Europe, they were relying on these incredibly inefficient methods to try and exploit that tiny, tiny difference.
Precisely. The main method back in the 70s was fractional crystallization, followed by a very slow process called ion exchange chromatography.
And fractional crystallization is?
It involved dissolving the mixed rare earth salts and then letting them slowly crystallize out. But because the properties were so similar, you had to repeat this. This process dozens, sometimes hundreds of times, just to get a usable degree of separation.
That sounds like something you do in a lab. It doesn't sound like an industrial process.
It was excruciatingly slow and expensive and capital intensive. I mean, U.S. operations at the time were producing less than 100 kilograms of high purity material per month.
100 kilos a month.
Less than that. And the cost was just staggering. We're talking upwards of $50,000 per ton.
Wow. So that kind of cost, plus all the toxic waste from these cycles, it just made it commercially unattractive.
Completely. It led Western companies to happily outsource the dirty, low-margin mining to places like China.
And that context, that's what makes Xu Guangxi's solution in 1971 so revolutionary. He didn't just improve the process.
He changed the entire paradigm. He fundamentally shifted it from batch-based mechanical repetition to a continuous flow chemical kinetics process. His breakthrough was the cascade extraction theory.
Okay, implemented using liquid solvent extraction. Can you explain that? How does that work?
So instead of crystallizing a solid, you use two liquids that don't mix. An aqueous or water-based phase with the rare earths and an organic solvent that flows in the opposite direction. Countercurrent.
Okay.
And the key is that because of that slight difference in atomic radius, that lanthanide contraction, each element has a fractionally different affinity for the organic solvent versus the water.
So it's not a one-step separation. It's more like a negotiation between the liquids.
That's a great way to put it. You run the liquids through a cascade, which is just a series of interconnected stages, maybe 30, 50, even 100 tanks. In each stage, the more attracted element jumps to the organic phase, while the less attracted one stays a bit longer in the aqueous phase.
And by repeating that over and over again, continuously,
you achieve this incredibly pure separation at the outlet.
And the stroke of genius, like we heard in the opening, was the application. Hydrochloric acid and plastic tanks.
Brilliant industrial engineering. I mean, by using simple inert materials like PVC plastic for the tanks and common hydrochloric acid, they replaced multi-million-dollar stainless steel reactors and exotic chemicals. It democratized the whole process.
It allowed them to take weeks of manual, high-cost work and compress it into just hours.
Hours of continuous flow. It immediately slashed production costs by 75%, down to a quarter of the American cost, while hitting 99.99% purity.
That is the foundational key. That's what flipped the entire script. It shifted the whole economic structure from this is too expensive and dirty to touch to
this is the world's cheapest and most scalable chemical process.
So here's the critical question then. Xu Guangxi's work, it wasn't a total secret forever. His theory was published. Why didn't Western companies just pivot and adopt this clearly superior, cheaper method?
That's a crucial point, and it really shows a broader blindness in Western industrial strategy at the time. There are a few reasons. First, just inertia.
Right, they were heavily invested in their existing equipment.
Exactly. And second, they just fundamentally underestimated the long-term strategic value of the resource itself. They saw it purely as a low-margin commodity.
So when the China shock happened and prices collapsed, they saw that as a reason to get out, not as a competitive threat they needed to counter with modernization.
Precisely. They saw the price plummeting and thought, this is a dirty business, let them have it. They completely failed to see that the new Chinese system was actually a technologically advanced, highly efficient process that had just eliminated the economic barriers to scale.
And the few places that did try to switch, they struggled.
Immensely, because the entire ecosystem, the process control, the precise engineering of the flow stages, the human capital, it was all missing.
And that failure, it really underscores the depth of the gap. You can see the legacy of it even today, 50 years later, when you look at modern Western attempts to rebuild this capacity.
The contrast is just striking. There was a report about a U.S. separation plant built for a staggering $439 million in 2025. It reportedly produces material that only achieves about 92% purity.
92%, which, for high-precision military applications like a Patriot missile, is basically useless. You need 99.9% or higher.
China was hitting 99.99% purity decades ago. That purity gap 2 orders of magnitude, that's not just a matter of machinery, it's a profound, systemic lack of chemical engineering knowledge.
It proves that knowledge is more than just a few formulas on a blackboard. It's the whole ecosystem, the process control, material science, and the specialized people that the U.S. just doesn't have in this field right now.
It really does. That initial scientific victory in the 70s was the non-negotiable prerequisite for everything that came after.
Okay, so the scientists solved the chemical puzzle, they broke the global price system. But that market-breaking surge in production, it required an equally strong political will to control it. So let's move to that next phase, the 4-decade campaign of centralized strategy, turning that scientific capability into a global monopoly.
Right, and this shift needed continuous, unambiguous strategic mandates right from the top. And that thinking was really formalized right around the time the China shock started to take hold.
You have Deng Xiaoping's famous 1992 statement, which just crystallizes the whole strategic thought process. He said, "The Middle East has oil and China has rare earths."
And that single statement, it elevated REEs from just a mineral commodity to a geopolitical tool. It wasn't just about digging something up, it was about leveraging a strategic asset. And that was reinforced by Jiang Zemin in 1999.
He gave the direct mandate.
With a direct mandate. The task was to improve the development and application of rare earth and change the resource advantage into economic superiority.
That's a national mission. That establishes these elements as a strategic tool for future industrial gain and ultimately for technological dominance. And to do that, they had to start with scale. And that means Baotou.
Baotou is the absolute epicenter. The Bayan Obo mine there contains an estimated 48 million tons of rare earth oxide reserves.
Which is what, a third of the world's total?
About 38% of all globally known reserves. That concentration of resource in one centrally manageable location, you just can't replicate that anywhere else.
But the masterstroke wasn't just having the resource. It was the industrial architecture, right?
Yeah.
Building the RE industry onto the existing Baogang steel group.
A colossal, half-century-old, state-owned enterprise.
And this integration, it gave them 3 massive advantages. It let them skip decades of traditional industrial ramp-up.
Yeah.
First, the human capital.
They had a skilled metallurgical workforce already there.
A large, skilled workforce already used to high-temperature processing and refining on a huge industrial scale. Second, they got instant infrastructure, power grids, rail lines, chemical handling expertise, which dramatically cut their initial costs.
And the third advantage is unique to Baotou's geology, integrated processing.
Yes, exactly. The rare earths are extracted as a byproduct of the massive iron ore mining operations. The iron ore is the main event, but the REEs are in the tailings.
So they don't have to ship the low-grade ore thousands of miles. It's processed right there. Right next door to the steel facilities. It creates these cost efficiencies that foreign competitors just can't possibly match.
So you go from a few thousand tons in the 70s to surpassing U.S. output by 86, and then a massive 120,000 tons by 2010. But before they consolidated, the sector was chaotic. You called it the Wild West. What did that look like?
The 2000s were just severe fragmentation. Thousands of small, illegal, polluting private producers sprung up, all driven by the lure of easy profit. And this led to oversupply, price crashes, and just rampant environmental abuse.
And this fragmentation, initially at least, worked against the central strategic goal.
It did, because local governments often resisted Beijing's attempts to consolidate. And the reason is simple. The small provincial enterprises paid taxes locally, which benefited the provincial budget.
While the big central state-owned enterprises, the SOEs, sent their revenue straight to Beijing.
Right. So local authorities would actually protect these small polluting entities to safeguard their own regional economies.
So how did the central government force the issue? How did they transition from that chaos to centralized control?
They used regulation as a weapon. This really accelerated between 2010 and 2020. The turning point was a diplomatic dispute with Japan in 2010.
When China briefly banned REE exports.
Right. And that revealed to the world and to Beijing the immense strategic power they held. But it also triggered a WTO case, which China lost.
Which forced them to get smarter about how they applied that leverage.
Exactly. They couldn't use explicit export quotas so easily anymore, so they started implementing stricter domestic measures that only the large, centralized SOEs could actually meet. Things like mandatory land use restrictions, a freeze on new mining licenses, significantly higher resource taxes.
And, crucially, stringent environmental protection inspections.
That was the hammer. Environmental cleanup became the vehicle for market consolidation.
Because the small, fragmented producers, they couldn't afford the capital investment to comply.
couldn't afford to comply with the new standards or pay the higher taxes, so it forced them to either shut down or be acquired by the state-owned giants. And that systematically led to the consolidation of all the mining and separation quotas around the big 6 SOEs.
And that campaign culminates in 2021 with the creation of the national champion, the ultimate centralization.
The State-Owned Asset Supervision and Administration Commission, SASAC, they approved the merger of 3 major SOEs, Chinalco, Minmetals, and Ganzhou, plus 2 key research firms to form the China Rare Earth Group.
And including the research firms in that merger, that signals the strategic focus is now firmly on the downstream high-value sectors.
It's a complete integrated national supply chain from mine to magnet designed for maximum efficiency and geopolitical control. And while they were doing this domestically, they were also securing their global feedstock supply. By 2019, China had become the world's largest importer of REE ores.
Wait, why ship rare earth ore into the country that has 38% of the world's reserves?
It's a 3-pronged strategy. 1, supply security. 2, mitigating their own domestic resource depletion. And 3, externalizing the environmental costs.
Which brings us to the Myanmar connection. This is specifically for the elements that are the most environmentally toxic to process, right?
Heavy rare earths, especially dysprosium and terbium. The mining for those relies on leaching methods that use massive amounts of ammonium sulfate. It's incredibly toxic for soil and water. So, when China imposed stricter environmental regulations in its southern provinces around 2016,
a huge amount of that heavy REE mining activity just shifted across the border into northern Myanmar.
Immediately. So they clean up their own backyard, but they secure the dirty, essential feedstock from abroad. It's a classic example of securing the high-value step, the complex chemical separation, while pushing the low-value, high-polluting extraction phase beyond their borders.
And that seamless strategy leads right into the next phase, establishing the industrial moat, the unassailable advantage in high-value manufacturing that locks in global dependency.
This is where that initial tech lead becomes true manufacturing supremacy. And the first major move wasn't R&D, it was pure IP capture. The acquisition of General Motors' magnet subsidiary, MagnaQuench.
A textbook case of strategic technology transfer.
It really is. The target, MagnaQuench, held critical patents for making neodymium permanent magnets, specifically a process that yielded this high-performance magnet powder. In 1995, a Chinese-led consortium bought the company.
And the regulators mandated a 5-year commitment to keep the assets in the U.S. What was the strategy during that period?
They immediately set up a parallel magnet manufacturing business in Tianjin and Ningbo. They used that 5-year window for an intensive, structured transfer of expertise, tooling, and crucially, the core know-how. By the time the commitment expired in 2002,
U.S. operations were shut down and everything equipment production lines was relocated to China.
It effectively decapitated the entire U.S. advanced magnet industry. They bought themselves what some analysts say was at least 10 years of technological evolution.
And that was the launch pad for their own massive internal advancement. Fast forward 2 decades, and now they're applying Industry 4.0 principles. Level 3 intelligent manufacturing maturity.
Yes.
So what does that actually look like on the factory floor? How does digital manufacturing translate into real superiority in a chemical plant?
It means hyper-precision and efficiency that humans just can't match. In that multi-stage solvent extraction process, purity is extremely sensitive to tiny fluctuations in temperature, pH, and flow rates. The AI-powered process control monitors hundreds of these data points in real time simultaneously.
So a human might check the pH once an hour. The AI is checking it every second.
And more than that, the algorithms can predict subtle shifts that might lead to impurities hours down the line, and then instantly adjust the solvent ratio or acid flow to compensate. They couple this with real-time spectroscopic analysis, where lasers check the chemical composition of the flow as it's happening.
So if purity drops by even 0.1%, the AI autocorrects before a human even sees a warning light.
Exactly. And then you have the digital twin modeling.
The virtual replica of the plant.
A complete virtual replica. It runs continuous simulations, modeling the impact of optimizing throughput or changing the raw material input before you do it physically. It minimizes downtime, finds bottlenecks, enables predictive maintenance. It's an unprecedented level of control.
And the measurable results of this are pretty stunning.
We're talking about consistent production consistency of 98 to 99% compared to maybe 85 or 90% in older plants. This digital approach gives them a 20-25% improvement in energy efficiency and a 35-40% faster overall processing speed.
And critically, it consistently hits that 99.9% purity threshold.
The non-negotiable threshold for high-stress applications.
And this tech advantage is then reinforced by an industrial policy that ingeniously turns the historical liability of pollution into a competitive advantage, the circular economy approach.
This is truly strategic. They create closed-loop systems using advanced membrane separation tech, which lets them reclaim up to 85% of their processed water and cut chemical consumption by 40%.
Fewer chemicals bought, less toxic wastewater to dispose of. That's just enormous cost optimization right there.
But it goes further. They monetize the waste streams. Instead of just creating toxic tailings ponds, they recover high-value byproducts. Iron concentrate gets fed right back into the adjacent steel production. They extract and sell fluorite. And most impressively, they extract high-value scandium from the residues.
Scandium, essential for aerospace components. So they turn a toxic byproduct into another revenue stream that subsidizes the cost of the main product.
It lowers the net cost of the final rare earth product. It embeds a competitive edge that foreign firms still struggling with older, dirtier methods just cannot overcome.
And the moat gets even higher when you look at the financial engineering, specifically the value-added tax, or VAT, refund mechanism. This is the economic weapon.
It's a textbook example of using trade policy as industrial strategy. Finished, high-value components, like rare earth magnets, they get a 13% tax refund when they're exported.
A direct 13% price advantage on the international market.
Instantly hyper-competitive. Now look at the other side of it. Taxes and cost disadvantages are maintained or even increased on the export of the raw materials, the oxides, the alloys.
So if a manufacturer in the U.S. wants to buy the refined oxide to make the magnet themselves,
they have to pay a premium for that raw input. So if you're trying to build a magnet factory in the U.S., you pay more for your materials, and then you have to compete against a finished Chinese product that is structurally subsidized by 13%.
It creates an inescapable double-digit cost disparity.
It forces global buyers to purchase the finished component from China. It ensures the high-value manufacturing, the know-how, the IP accumulation. It all stays within China. The whole policy is designed to capture the maximum value.
And finally, that moat is deepened by a massive coordinated state commitment to R&D and talent development.
The scale is profound. Government spending just in Baotou alone exceeded 8 billion yuan between 2020 and 2024. And look at the allocation. Almost 80% was dedicated to modernization and environmental improvements. They were strategically funding the transition to cleaner, cheaper, digitally controlled production.
And the research infrastructure. Just contrast the U.S. approach to the Chinese commitment.
The contrast is stark. China operates at least 4 large-scale national laboratories dedicated exclusively to rare earths. The biggest one was established back in 1985. These institutions work directly with the major processing facilities.
And the U.S.
The U.S. currently maintains 0 national labs specifically dedicated to rare earth elements.
4 versus 0. That tells you who's setting the agenda for the future.
It really does. And then there's the human capital. At least 39 universities in China have dedicated rare earth programs, producing thousands of specialized graduates every year. That concentration of talent is another reinforcing moat.
And this all translates into intellectual property. The patents tell the story.
The IP dominance is staggering. China files roughly 30 rare earth patents for every 1 U.S. patent. They've filed more rare earth patents than the rest of the world combined.
Can you give us an example of a future-proofing technology they're mastering that really highlights this depth?
Their intense focus on grain boundary diffusion technology. This is a very sophisticated process that deals with the cost and scarcity of the heavy rare earths, like dysprosium.
Which you need for thermal stability in magnets.
Right. Traditionally, to make a magnet resistant to high heat, you had to alloy the entire magnet, the whole bulk, with expensive and scarce dysprosium. Grain boundary diffusion changes that. After the core magnet is made, the heavy rare earths are infused only into the surface layers of the individual magnet grains.
So you get the same performance, but you use dramatically less of the expensive hard-to-source element.
Exactly. You can reduce dysprosium usage by 50% or more. By mastering this, they guarantee their high-performance magnets maintain quality, they reduce reliance on volatile sources like Myanmar, and they ensure long-term cost sustainability.
Okay, so we've seen how 4 decades of policy, scale, and integrated technology were built. Now let's get to the present. The result: near total market control, and how that translates into strategic leverage against global defense and green energy. This is the geopolitical choke point.
The scale of control is undeniable, particularly in the high-value downstream sector. China produces somewhere between 85 and 90% of global rare earth permanent magnets.
But the value distribution, that's where the real leverage is.
Yes. For the critical high-performance magnets, the kind you need for EV motors, high-efficiency wind turbines, defense actuators, Chinese manufacturers command roughly 90% of global output. That dependency extends into every corner of the high-tech economy.
And that capacity is reinforced by controlling the specific ingredients.
Yeah.
This is the dysprosium and terbium choke point.
This is maybe the ultimate leverage point. As we said, high-performance magnets have to keep their strength when temperatures rise. Without doping with dysprosium and terbium, the magnet demagnetizes above about 65 degrees Celsius.
And China's control over those two specific elements is nearly total.
It's virtually 100% of the global supply of separated terbium and dysprosium. They are geologically scarcer and just incredibly difficult to separate economically outside of China's specific deposits and their highly refined, optimized processes.
Which means foreign magnet makers are basically stuck making low-performance, low-margin products.
They can't compete in the high-value sectors without Chinese inputs. And this control translates into profound defense system vulnerability for the U.S. and its allies.
Rare earths are indispensable to military supremacy, but the U.S. domestic supply chain is just dangerously brittle.
The reliance is institutionalized. I mean, take the F-35 fighter jet. It relies on these magnets for its electric drive systems, its actuators, its advanced radar. Virginia and Columbia-class submarines use tons of them. Tomahawk missiles, JDAM smart bombs, Predator UAVs, they all depend on these materials.
And we should also mention the samarium cobalt niche, which is vital for the most extreme environments.
SMCO magnets are essential for surviving extreme heat. While high-performance NdFeB magnets fail above 200 degrees Celsius, SMCO magnets maintain stability up to 550 degrees.
Which makes them non-negotiable for things near jet engine afterburners or in high-frequency radar.
And because China controls the samarium supplies, it maintains a dominant share in SMCO production as well. So even in the most sensitive military applications, the supply chain leads right back to their integrated ecosystem.
And the regulatory situation just confirms this. The U.S. defense industry have to rely on special waivers to bypass regulations against sourcing foreign components.
Which is an implicit confirmation that Chinese origin components are integrated into American weapon systems. And the latest strategic maneuver is the targeted use of export controls. The 0.1% rule.
Implemented in 2025-2026. Licensing restrictions on 7 critical heavy rare earths.
And the sheer scope of the regulation is the deterrent. It requires government approval to export any product containing more than 0.1% Re by weight. And crucially, exporters have to declare the intended end use of the product.
Which gives Beijing a powerful tracing tool and a lever for targeted future restrictions. It's a mechanism for comprehensive economic statecraft.
Analysts call it strategic deterrence via supply disruption. It's like the 1973 Arab oil embargo, but applied to high-tech manufacturing. By influencing the sale of tiny, crucial components, China gives itself potential influence over an estimated $135 to $270 billion worth of high-tech products globally.
And we saw a perfect illustration of this vulnerability with that anecdote about the Detroit EV assembly line.
That event, a multi-billion-dollar river of industry paralyzed because a tiny magnet in a seat adjuster was delayed by new export licensing. That perfectly demonstrates the concept. The inability to move a seat renders the entire vehicle legally unsaleable.
And that one component is controlled by a geopolitical rival. This structural control also means China effectively controls the pace and cost of the global transition to green energy.
The demand is explosive. EV motor demand for these magnets is projected to double by 2025. A single EV motor needs several kilograms of them. A modern offshore wind turbine needs tons. If China controls the core component, it controls the global pace and cost of new energy infrastructure.
So finally, what's been the geopolitical response? There's recognition of the problem, but what are the challenges in closing that gap?
The response has been recognition followed by, urgent diversification efforts. The U.S. has signed critical minerals agreements with allies like Australia, an $8.5 billion deal, and Japan trying to build external processing capacity.
But those supply chains, they take years, if not decades, and billions of dollars to establish, and you still have all the regulatory and environmental challenges that China systematically offloaded.
Exactly. You can find the ore. That's the easy part. The hard part is mastering the continuous flow chemistry, building the integrated industrial parks, training thousands of specialized engineers, and hitting that 99.9% purity threshold economically. That process is measured in decades.
Which explains this short-term tactical move, the U.S.-China G2 truce in October 2025, to postpone some of the controls.
It's a short-term measure that just highlights the absolute urgency of the situation. The U.S. needs the current Chinese supply while it races to establish its own resilience, a race where it's currently 50 years behind schedule.
It's a compelling, comprehensive story. We started with a brilliant chemist in a modest lab in 1971, solving this impossible chemical puzzle with simple materials.
And we ended with AI-controlled factories wielding global geopolitical power through industrial choke points and trade policy.
The profound implications of long-term, state-driven planning are just undeniable. This is a story of strategic patience. And it shows the ultimate leverage in the 21st century isn't just about who controls the ore. It's about who have the comprehensive, integrated, technologically advanced capacity to refine, alloy, and manufacture the crucial high-performance components.
And by integrating that scientific dedication, that vertical industrial efficiency, massive R&D, and targeted economic policy, like the 13% EAT rebate China, successfully transformed what was just a geological advantage into long-term, unshakable technological and geopolitical leadership.